We now consider trajectories. Trajectories are the profiles that we reconstruct given the tangent vectors of some parametrized paths. You may recall that up to now we've been given the vector r, which generated a number of concepts or notions. We generated the notion of the tangent vector, and we said that the unit tangent vector would have been the vector u, which is your vector r dot divided by its magnitude. There were the notions of your normal at some point, and in 3 dimensions you would have had the binomial, the vector b. In this case, what we are given are the tangent vectors, which we're going to refer to as the vector field. And what we need to do is to reconstruct what the paths would look like for which these given vector fields are the tangent vectors. Okay, and the reconstructed paths will be the trajectories. So these trajectories will be the equivalent of the vector r, but we will see eventually that it will not be a single vector r, but rather a family of vector r's, which will look like a profile, which we then refer to as the trajectories. So this is the beginning point. Suppose we are given a vector field, and keep in mind that the vector field represents tangent vectors. So given a vector field, say vector v, given by v1, v2, and for now let's keep this to 2 dimensions, and obviously this may be extendable to n dimensions. But there's an advantage that we have in 2 dimensions which we don't have in the higher dimensions. We'll see that later. And each of the components in this vector field would represent a component of the tangent vectors, right? So here, then what we have is that the first component, vector v1, is the derivative of the x component of vector r of your path. So this will be dx dt. T again is your parameter. The second component, v2, will be dy dt, and so on if we have a higher dimension. And using these various equations, which essentially are differential equations, we need to reconstruct the vector r. In other words, we need to determine what x, y, z, etc. are. These, remember, then are the components of vector r. So vector r, if you recall, was x, y. Each of these are functions of t. What we have now are the r dots. Okay then. So let's do this by way of example. Suppose in the first example, and that's not a very interesting notation for example, we are given that the vector field v has components x minus y. So given what we have above, we have i.e. that dx dt is equal to x, and simultaneously dy dt is equal to minus y. So these are 2 simple differential equations to solve. We can either solve them independently, so these will be 2 separate differential equations. We could solve for x in terms of t, y in terms of t, or, and this is only possible in the 2-dimensional case, 2-dimensional meaning there are 2 components, referring to the xy system of xc's. We can write these 2 equations as a single system by noting that if we divide the one by the other, we eliminate the t. So if we divide these 2 equations, what we get is the following. We get that dy dt divided by dx dt So here we have dy dt over dx dt equals minus y over x. By the chain rule, what we have is that dy dx equals a very simple first order differential equation minus y over x, which can be solved by variables separable. So what we have is then one of these should have been dy. I guess that should be dy. So we have that dy over y equals dx over minus x. So if you were to separate this, this becomes dy over y equals dx over minus x. We can easily integrate both sides, and if we do so, what we end up with is that on the right hand side we have the ln of the mod of, left hand side is ln of mod of y equals minus the ln of the mod of x. In fact, it would be better to write the integration constant also as a ln, so this would be the ln of c. We are assuming c is a positive constant. If you eliminate all the log functions, take the log x to the left hand side, what we get is therefore that mod of xy or xy itself equals c. I should say plus or minus, because we've taken, we've dropped the logs, so there should be positives all over. Now for whether c is positive or negative, we know these give us hyperbole, a family of hyperbole. So these in fact are a family of hyperbole. And if we were to sketch this on an xy system, and since c is an arbitrary constant, if c is positive, what we end up with are hyperboles that do that. Okay, and if c is negative, we have hyperboles that do that. What we need to be careful here are the profiles. And that is that we've constructed this hyperbole, but what we need to also be aware of are the directions that these hyperboles take. And that we need to do separately. So we know that the shapes of these profiles, the shape of these trajectories are general hyperbole. What we will do now is look at the exact form of the profiles by taking the vector field V and considering component by component, or as particularly what they would look like in a specific quadrant at any given in any given case. Okay, so let's go back a bit. We said that the vector field V has components x minus y, and in your Cartesian system, we know that in the first quadrant, the x and y's are both positive. In the second, of course, the x is negative, y is positive, etc. So in the first quadrant, we want to determine the directions of these vector fields. So this is now in the first quadrant. Okay. Now in the first quadrant, the x and y are both positive. So that indicates the signatures, the signs of the x and y coordinates in the first quadrant. What effect would that x positive and y positive have on the signatures of the components of the vector field? So if we were to impose x positive, y positive into the vector field, you notice that if x is positive, then the vector field would have the first component positive, and the second component of the vector field is minus y, but since y is positive, negative times positive is negative, so the vector field would take on those signatures. Now these are vectors, so that will be the direction of the vectors in the first quadrant. Now if a vector has a positive negative signature, then it would be the x's being positive and the y being negative. That means we'll have vectors pointing in this direction. Okay. In the second quadrant, we have the x's are negative and the y's are positive. Still positive. So therefore, the consequence on the signatures of the vector field, keeping in mind that the vector field V is still x minus y, but now the x's are negative and the y's are positive. If x is negative and y is positive, then the vector field, if you impose x negative and y positive into the vector field, then the x becomes negative, and the second component is negative y is positive, so negative times positive is negative, so the vector field takes on directions negative, negative. A vector field with components negative, negative would be pointing down towards the third quadrant. So that in the second quadrant, we'll have vector fields that will be pointing in those directions, like so. I should say that vector fields that have the signs positive, negative point towards the fourth quadrant. That would have been in the previous case. In the third quadrant, the signatures of the x and y's are negative, negative. In the third quadrant, x is negative, y is negative. What consequence does that have on the signature of the given vector field? Well, if x is negative, then the first component of the vector field will be negative. The second component of the vector field is minus y, but y is negative, so negative, negative, the second component will be positive. Now, a vector having negative, positive signature will be a vector pointing towards the second quadrant. So that in the third quadrant, the direction of the vector fields would be pointing towards the second quadrant. So that when we go back there, that will be the general direction, like so. The fourth quadrant. In the fourth quadrant, the x is positive, the y is negative. What consequence does that have on the vector field, or at least the directions of the vector fields? Well, here what happens then is, again, vector field V is still x minus y, but the x is positive, so that is positive. The second component of the vector field V is minus y, but y is negative in the fourth quadrant. So negative y gives us negative, negative y, negative, negative, which is positive. So that in the fourth quadrant, the vector fields will pointing towards the first quadrant. Let's go back to the fourth quadrant. This is the consequence. If we put these arrows back into what we had above, then the hyperbole that we sketched earlier on would have directions coinciding with what we just had. So that therefore, what we have is the directions would be, well, I should indicate that. So this will be pointing towards there, there, there. In the second quadrant, it will be pointing that way. In the third quadrant, I'm imposing the directions that we just constructed, and in the fourth quadrant, we have generally those directions. And then, of course, one needs to determine the directions of the vector field V along the axes too. For example, in the positive x-axis, or along the positive x-axis, y is equal to 0 and x is positive. So let's discuss that a bit, just to get the exact direction in the along the axes. So for example, on the positive x-axis, right? We know that we have x's are all positive, we have the x's are positive, but the y coordinates are all 0. Therefore, what would the vector field v look like? Well, the vector field v is still x minus y. So x minus y will have the signatures positive, minus y will be minus 0, so it's 0. Now, what are these vector fields? These are vector fields that have direction positive and y coordinate 0. So these are vector fields that do that. So when we go to the positive x-axis, the vector fields will have that as a direction, i.e. So going back up there, so there what we have is those arrows there. And similarly, when we check each of the other three axes, you've got y positive and x negative there, x0 will have these directions, and you can check that this should all be falling in line with the general profile, like so. So the shape is given by the solution of the equation. The direction of the profiles, the curves, are given by us going through each of the components separately. The next example, there we are. What we need to do at this point, before continuing to the other three quadrants, is to determine what happens on the line separating sections 1 and 2. And that is that line there. Okay? And that is the line y equal to x. So on the line y equal to x, we also have certain directions of these vectors, the profile. And if we impose y equal to x on the vector field, then as a consequence of that, the vector field will have the following signatures on that dotted line. So if y is equal to x, the vector field v would be 0 as the first component, and x and y both being positive, we have that kind of situation. So what we have is the vector field v having the profile 0 positive, and any vector field with components 0 positive will be pointing up towards along the positive y-axis. So what happens on the line, if you go back there, is we get arrows going up like so. Okay, now let's try to put that together, and make it look interesting. So this is what's happening in that first quadrant. We've got vector fields that are pointing that way, and then pointing upwards, and then pointing that way. And we have infinitely many of these vector fields. What happens then is we've got trying to put this profile together. What we have is the vector field going towards the positive quadrant, the first quadrant, then straight up, and then taking a turn that way. So it's doing that kind of thing. There we are. So this is what that first quadrant should look like in terms of the directions of its arrows. And we can do this for each of the other three quadrants. It's a bit trickier in the other quadrants because we may have x positive, y negative, and vice versa. But then what is the actual shape of this profile in the first quadrant? Well, that we'll have to solve some differential equations to do that. Okay. But if we were to put this information together for the other quadrants, so I will just say here, similarly, what we get in the other quadrants, we put all of this together, right, is we get arrows that do that and that. Okay, this is what we've obtained up there. And if we split the second quadrant into three sections, well, we'll find that the vector fields do that, and along the line y equal to minus x, It will be pointing downwards, and then in this third section it will be doing that. And similarly, when we do the third quadrant, we get something interesting. We get vector fields that point that way, straight up, and also down that way. Okay? And in the fourth quadrant, we get vector fields that will do that, if you have to do the whole profile together, and that kind of thing. So we'll have to do each of the four quadrants as I've discussed the first quadrant. And when you put all of this together, what you get are profiles that look like this, if you join the arrows. And that too, if you join the direction of the arrows. And here too, we get things that do that. Oh, sorry, there's a big mistake here. Sorry, I need to redo this. Yes, so this, in this quadrant we have that as I've done. And if you put together what happens at the bottom, the directions tend to go that way. Put that together, and then we construct that. And you could do similar things along the axes and so on. What the exact shape of these would be, well, that will be determined by solving the differential equation. Right, what are the exact shapes of this? So what we have is that from the vector field V, right, just recall the vector field V is again x squared minus y squared 2xy, and the first component is equal to dx dt, the second component is equal to dy dt, and if you divide this dy dt by dy dx, we get dy dx equals 2xy over x squared minus y squared. This, if you recall, is a first order homogeneous first year type differential equation, which you would solve by letting y equal to vx, if you recall all that. And if you do that, you get v plus x dv dx equals dy dx by the product rule. You impose that on the differential equation without getting into too much detail. What you end up with is x dv dx will equal v into v squared plus 1. This is after some simplification. You can do that. 1 minus v squared. Now it's variable separable, and once you've separated them, used partial fractions, etc., you find that finally you get y is, and putting back y equal to vx or v equal to y over x, you get y is equal to a into x squared plus y squared. And if you do a little more of these simplifications, what we get is the following. Just to say what exactly the shape would be, we will get ay squared, therefore, minus y, if you take the y to the other side, plus ax squared equals 0. We can divide throughout by a, therefore y squared minus minus 1 over a times y plus x squared equals 0. If we complete the square in the y coordinates, what you get is y minus 1 over 2a all squared plus x squared. So in completing the square in the y coordinates, we've introduced an extra term, 1 over 2a all squared. Let's do it on the other side. So we get 1 over 4a squared. This is a circle whose center is 0, 1 over 2a, and radius 1 over 2a. So this is a circle, and center, with center x coordinate 0, y coordinate 1 over 2a, and radius 1 over 2a. So all of those circles that all of the profiles that we constructed earlier on, these profiles, so these profiles are in fact circles, and circles each of whose equation is given there. And if you take a single one of these circles, well, a circle, if A is positive, some general value A, then a circle center 0, 1 over 2A would, for example, be, there's a center 1 over 2A, the radius is 1 over 2A, it will be a circle that does that. Okay, center 1 over 2A, radius 1 over 2A, so it passes through the origin, supposed to pass through the origin, there. When you get to a three-dimensional example, this, I suppose, if you had access to computers and so on, you could get the exact direction of these profiles. All we can do in the three-dimensional or in high-dimension case is to determine the equations of these profiles, which would of course be include a parameter as we go along. So remember, a path in three or high dimensions can only be expressed in parametric form using a parameter, say t. Okay, so let's do an example in 3 dimensions. Suppose we have an example. Perhaps this should be in a better color. In example 3, we say the vector field V. So there'll be 3 coordinates, so there'll be a third variable involved. Suppose minus y x1, and of course this is equal to dx dt, dy dt, dz dt. And we want x, y, and z, which will give us the vector field, vector r, which is x, y, and z. It'll be in terms of t. Right, so we get that dx dt, for example, is minus y, dy dt is x, and dz dt is the constant 1, for which we need to solve for x, y, and z. Starting with the first equation, the problem with the first equation and the second one is it's an equation involving 3 variables. The first one, for example, has x, y, and t, so we need to eliminate one of the variables. One way of doing that is to take the first equation and first differentiating it before trying to solve for x in terms of t. So if you take this and differentiate with respect to t, you get d2x by dt squared equals minus dy dt, so that d2x by dt squared equals minus y. Right. What does it mean? What we have here is we can solve this differential equation using d operators. Note that this is d squared plus 1 operating on x equal to 0. You are very familiar with that. So therefore, x would be, where d, of course, is d by dt. So x is equal to a constant cosine t plus another constant sine t, like so. We can now solve for y very easily. If you put this into the second equation, therefore dy dt would be equal to, well, you could either use the second equation or the first equation. In fact, let's rather use the first equation to solve for y. By the first equation, y is equal to minus x dot, and that is equal to, just differentiating this, minus a sine t plus b cos t. And what's the z coordinate? The third equation is rather straightforward. From dz dt equal to 1. Cross multiply, you get dz equals dt. We get that z is equal to t plus some constant k. So there we have it. We have x in terms of t, y in terms of t, z in terms of t, and vector r would be, of course, x, y, z. It's easy to show, in fact. Oh, perhaps I should do that. That you can, in fact, we can show, and this is using first year methods, we can show that x can be written as a single cosine function, r cosine t minus some alpha. Similarly, we'll get that y is equal to r sine t minus alpha, and z, of course, is just t plus k. And this, if you choose constants in a particular way, you have the cosine t, cosine of t, sine of t, z equal to t. This, you may recall, have the helical shape, like so. Right, we'll stop the lecture there on reconstructing profiles or using vector fields, and we'll end with this last example being the following.